Hello, everyone, and welcome back. This video is meant to be just a brief follow-up to what we talked about in the previous video. And I'll remind you that we introduced the concepts of exponential growth and exponential decay. In particular, we saw these things come from a differential equation. In this lecture, we're going to continue talking about differential equations and look at a very particular type of differential equation called a separable differential equation. So let me show you what I mean by sharing my screen. Now, I'll remind you that in the previous video, we had this exponential growth and decay model that looked like this. And the way that we solved this thing was by dividing off y. So we had 1 over y dy dt is equal to k. And then what we did is we slapped an integral around this thing. And we got the following. Now, informally, if you sort of treat these differentials, the dy dt's, as fractions, you can kind of see here that you have it on the top and the bottom, and you essentially just get an integral of 1 over y dy is equal to the integral of k dt. Now, if you actually solve this, you will find that you get the ln of the absolute value of y is equal to k times t plus some constant. And the constant comes through because we're talking about indefinite integrals. But if you go back to the previous video and you look at what we did there, we used substitution, but we essentially got to the same place. So this step from here to here, we didn't really need to introduce any substitution. What we really needed to do was sort of treat these dy by dx's or dy by dt's as just sort of fractions. We have an informal way of moving through this. Okay, so then how about if I give you a general ordinary differential equation? So if I give you something that looks like this, again, you have some quantity y, which depends on time t. This could be x if you wanted it to be 2, and its slope is given by some function of t and y. Now, in the previous case, we didn't have any t dependence, right? So this told us it doesn't matter when you start the clock, because the only thing that matters maybe was the population of the biomass that you're interested in, or the population of the disease, or the chemical concentration. Whereas here, this is telling you that you could also have time dependence. So for example, if this was modeling a disease again, the time dependence could be seasonal variation. So you could have a larger slope or a larger positive slope for y in terms of the disease, maybe in the summer when we know that diseases spread easier, or sorry, in the winter when they spread easier. And then when t is represented by the summer months, then you could have a smaller slope representing the fact that diseases are harder to spread sometimes in the summer. This is just one such example. But essentially, solutions to this are still functions y of t, but it's much more difficult to solve this thing. Now, we are going to focus on a particular version of this differential equation that we can solve, at least to get implicit functions of y. And I'll show you what I mean in a moment. But let's consider the following. Let's consider a function, f of t comma y, so that this could genuinely be a function of t and y, but it breaks up. It can be written as two functions multiplied by each other. So for example, when we had this one, ky, which was our population growth model, we had maybe g of t is just equal to 1, right? There was no real time dependence in here. And h of y is just a constant times y. It's a linear function of y. Now, of course, this scenario that I'm spelling out right here is much more general. This is what's called a separable function. It says you can separate out the variables. So f is a function of two variables, t and y. But when you look at it, you can see that you can sort of separate the variables out into a function just of t and a function just of y. And so why is this important? Well, this tells us that if we're given this differential equation, I'll skip right to it being separable. So g of t times h of y. We can collect all of the t's on one side and all of the y's on another. So I'm going to treat dy dt as a fraction. And so I'm going to have 1 over h of y dy is equal to g of t dt. Okay, so I multiplied the dt up and I divided the h of y off. And this is, of course, assuming that we actually can divide h of y off, right? So assuming h of y is not equal to 0, we have to restrict ourselves to this part of the domain. Okay, now we can slap the integral back on that thing. And we can, at least in theory, get explicit solutions for this thing, right? So now, of course, we've reduced the problem of solving this differential equation to one that is just a straight integration problem. Okay, so let's look at an example here. How about I give you a differential equation and I ask us to solve it. So dy dt is equal to 1 plus y e to the t. And I'm going to put a stipulation on here that I'm only interested in the cases where y is larger than -1. Okay, well then, if we pose this in terms of the separable equations we just had above, we get f is exactly the right-hand side of this differential equation, which tells us that g is e to the power of t, and h is 1 plus y. So that tells us that this differential equation is itself separable. We can separate out the t from the y components of this thing. And furthermore, we see that h of y is bigger than 0 in this domain restricted region of y larger than -1. So let's go ahead and let's solve this differential equation using what I have above. So I have dy dt is equal to 1 plus y e to the t. Now I multiply up the dt, I divide by the 1 plus y, and I get, let's say, dy over 1 plus y is equal to e to the t dt. I can slap an integral on that. And now what I have is the integral of 1 over 1 plus y and the integral of e to the t. And you can see that they have different integrable variables. In the left-hand side, it's y. In the right-hand side, it's t. But nonetheless, we can solve these things. The first one, you might have to do a substitution of 1 plus y, but I'm going to skip that step. And I'm going to say that that integral is actually equal to the natural logarithm of 1 plus y. And I didn't put absolute values on it because I'm assuming y is larger than 1, right? So this is no absolute value because y is larger than -1. So that thing is always positive. And this is equal to integrating up e to the t. We saw this 2 lectures ago. This is just e to the t again. And don't forget that plus c. So right now, we have a implicit equation, right, that tells me what the value of y will be as long as I know what the value of t will be, right? I can undo this thing and I need to have equality here. But of course, it would be much better if I just had a function y of t. So let's keep going. Let's undo this logarithm. And in this case, I got e and then e to the t plus c. And so now you can see that I get y of t is equal to -1 plus e to the c e to the t. So it's a very ugly function, right? It's doubly exponential. And typically what we do is we like to write the e to the c as just a new constant, say a, right? And we saw in the previous video that we can find a as long as we're given some sort of initial condition. So if I know what y is at, say, time equal to 0, then I can find, say, what a would have to be. In this case, we weren't given an initial condition, so we're not going to worry about it. Okay, so let's look at one more example here. Let's imagine we're given, or we're asked to solve the following. We have this equation, t over y times y squared plus 1 divided by y times t plus 1. Well, in this case, f of t and y is just the right-hand side. And we can see that this can be separated out into two functions. One that is just a function of t, that's t over t plus 1. And the second one is equal to y squared plus 1 over y. And this tells us that my equation has to be separable. I can turn it into a function of t multiplied by a function of y. And so that means that I can use the fact that this is separable to solve this differential equation. So let's write out the differential equation one more time. Sorry, I keep putting x in here. It should be t. So here's the differential equation. Then we divide by h, and we multiply by dt on both sides. This gives me y dy over y squared plus 1. And this is equal to t over t plus 1 dt. And we're going to do the same thing that we've been doing over and over. Let's slap an integral on that thing right off the bat. Now, I'm going to leave the actual integration to you to fill in the blanks. But in the left-hand side, you can substitute for y squared plus 1. And in fact, you're going to get 1/2 of the logarithm of y squared plus 1. Now, y squared plus 1 is always positive, so I don't have to worry about the absolute value anymore either. And in the case of this integral, I will show one intermediate step. You can rewrite that fraction as 1 minus 1 over t plus 1. So all that I did is I took the fraction t over t plus 1 and I broke it into this 1 minus 1 over t plus 1. So this is a little trick. It's hard to notice, but it just sort of comes with practice. But now these are things that I can integrate independently. And so in this case, now what I can do is I can find that I get t minus ln of the absolute value of t plus 1 plus c. Now, here's the real heartbreaker of all of this. You can try and multiply through by 2. You can take an exponential. And all that you're going to wind up doing is solving for y squared. You won't be able to solve for y, right? Because if you want to solve for y, you need to take plus or minus with the square roots. And so we are going to leave this as an implicit equation, right? So it says that, you know, if you give me a value of t, you have to find the value of y. In our case, it'll be values, one positive, one negative, for which you can satisfy this equality. So it is a solution, right? It's an implicit solution to the differential equation. And in my opinion, it gives a lot more information than the derivative version with the actual differential equation here at the top. But it's still kind of complicated, right? Because it's still an implicit equation, and implicit equations are much harder to work with than, say, just y of t is equal to whatever. Okay, so that's all that I wanted to talk about in this video. Is just a brief introduction to more complex differential equations and how we can use integrals to solve those as well. Again, we need to develop tools in order to solve for more complicated functions. That is, put in different functions for G and different functions for H in order to be able to integrate them with more robust methods. And that's what we're going to talk about as we continue to progress through this class.